The derivative tells us the slope of the tangent line to the graph of a function at some point. It also tells us the instantaneous rate of change, and it also tells us we've got some work to do, because here's the definition. That's one of the common notations, and we're going to take the limit for h near 0 of a nasty fraction with h on the bottom and the difference of the two values of f on top. So the first thing we can do with this, without actually doing a lot of calculation, is to notice something. The rate of change of position is what is commonly called velocity. And the rate of change of velocity, that's actually the definition of acceleration. And so there's this metaphor that we can use. The derivative is speed. Well, it's assigned speed. This is positive, this is negative, or this is positive, this is negative. And the derivative of speed, or of velocity, is acceleration. Oh, I dropped my pen. Acceleration due to gravity. Pardon me a second. Went too far. Okay, so let me just kind of write that down, is that the derivative of position is velocity, and the derivative of velocity is acceleration. And now I'm using the other common notation for derivatives. T is the variable t, usually is time. We should define that more carefully. S is position, so ds by dt is velocity, and dv by dt is acceleration. Velocity is a function, acceleration is a function. So that's a big theoretical thing, but what's the point of having all this theory unless we can actually do it? And we went through and had this rather laborious process in doing the logarithm. And so let me just set up a table here. So with the logarithm, we went through a laborious process that convinced us, or at least convinced me, I hope it convinced you, that the derivative of logarithm is reciprocal. And that's what makes it natural. It's just 1 over x. And so if you look at the graph of logarithm, the slope of the tangent at any point is 1 over the x-coordinate, which means when x is 1,000,000, the tangent is almost horizontal. So anyway, well, let's put this in our table, that the derivative of natural log of x is 1 over x. Okay, now, what about other functions? There are a lot of other functions that come up in applications, and I'm going to kind of leap ahead a little bit to something that we can see more exactly, analytically later, which is the derivative of the exponential function. And this is one of the most amazing things in calculus. This is one of the most amazing things in the universe, never mind just in calculus, that if we look at the exponential function e to the x, the derivative is e to the x. This function is its own derivative, which is why it keeps coming up so much in applications, as we'll see later when we start to look at some of the applications. So you're just going to have to be patient. Okay. Another thing that we look at a lot are polynomials. And let's just kind of get a flavor for the polynomial situation here. Let's look at the function f of x equals x squared. And we can say some things about the derivative straight away without doing too much work, because we know that that's a basic shape, and the basic shape. And we can see the tangent lines, and so we can say that if x is positive, that means that f prime of x is positive. Because if you just look at the tangent line on this side, that has a positive slope. It's getting steeper too, that's something worth making note of, but the real idea is that the slope is positive. And on the other side, if x is negative, f prime of x, well, if you look at that tangent line, then it has a negative slope. And so whatever we do analytically, it ought to correspond to this. Sometimes this is enough. You'd be surprised how often this is enough, especially in a lot of the applications that we'll see once we have the mean value theorem. But for the moment, we're just going to use this to kind of check our work. It's a partial check. We're not actually seeing that the derivative is 4.2 or whatever, we're just going to say, oh, it's supposed to be positive, and it came out 4.2, so no contradiction there. That's a little bit of comfort, I hope. Okay, so we're going to take the derivative of x squared, and that means we have to go back to this, and we're in the situation where we can't just say, hey, you know, x is close to 3, so x squared is close to 9, so x squared minus 1 is close to 8. And the reason is here, when we're looking at this difference quotient, which is the same thing you studied in pre-calculus, the top is near 0 unless you have a discontinuous function, and the bottom is near 0, and so the limit is anybody's guess. Well, we have some things going for us here, and we're going to take advantage of what we know. So the idea is what you're going to have to do is to do some algebra to put the limit into a form where it's obvious. So there are two steps to this, and they're very distinct. One is the algebra step. You might have done this in pre-calculus. And the other is, oh, look, I have this obvious limit. And trust me, when we get there, it's going to be an obvious limit. So let's look at the algebra. We need to do this to this. So do the parentheses first. So it's going to be a big old nasty fraction. It's not very dramatic, is it? But it's a big old nasty fraction. And let's quick put h on the bottom. Remember, h is near 0. H is not at 0, so you don't have to worry about anyone getting hurt. H is near 0. So that's the bottom, same as up here. And the top, I'm going to do the actual function that we're talking about. So the function is squaring. So when we have the input x plus h, we'll square x plus h. And when we have the input x, we'll square x. So doing the parentheses first, which is a real smart way to do algebra, we get to here, we have a square and a square, and then we'll fill in the blanks, and I'll do that in a different color. In one case, we're doing this with a little bit of a horizontal move, that's at x plus h. Remember, h can be negative as well. It's near 0. That doesn't mean it's positive, it means it's near 0. So in one of those, the first one will have x plus h, and in the second one we'll have x. Now, a lot of people say that this is an extra step. They're wrong. A lot of people skip this step, and then they're wrong because they can't do it right without this step. So let's do it. So I've taken the idea of the difference quotient. I'm not even doing the limit right now. And I've said, oh, it's a difference of squares. And so I'm going to write something squared, and then h on the bottom. Okay, so now we have to do the algebra. And this is something that happens with all polynomials. Luckily, we don't have to do this very much, and I'm going to show you why before we end. But let me just continue here. And what I'm going to have to do is multiply out the two squares. Now, one of them is pretty easy, x squared. So I always do the easy stuff first, because that way, if I get interrupted, I at least get some partial credit. Okay. The other is what I'm going to have to do is take this x plus h quantity squared and multiply that out. Well, that's algebra that people studied a long time ago, x squared minus 2xh plus h squared. So sorry it's a little small when I scan this. I hope you'll be able to read it. But there it is. I haven't done anything yet. I've just organized. I guess I did. I squared out x plus h. Forgive me. Okay. Now, this is something that always happens when we're working with polynomials. Always. And it's not just the one-term polynomials. You have x cubed minus x plus 4. What I'm about to show you is always going to happen, which is we get an x squared, and then we subtract off the x squared. And so the original function gets subtracted off every time unless you've made an algebra mistake. So that's a kind of a way that you can check yourself. So let's cancel out these x squareds. Pretty easy. And then we'll go on to the next step, which is just gather up the terms on top. The term on the bottom is all gathered up for us, right? So we'll gather up the terms on top and see what happens. I'm sorry, I've discovered a mistake here. I got ahead of myself. This should have been x squared plus 2xh plus h squared. So that'll be plus when I scan this, and it should have been plus, so we're in good shape. Okay, now what's left here is 2xh plus h squared. So I've done the algebra, subtracted off the original function because it appears twice with different signs, and we're left with 2xh plus h squared, which we can factor, and I will do so. So the bottom is still h. We haven't done anything to the bottom. That's nice. And when we factor 2xh plus h squared, what we get is 2x plus h. Now comes the fun part. Oh, this has been fun all along. Don't give me that. The fun part is, remember, h is near 0, but not at 0. And so the h's cancel. Boom. This happens every time unless you've made an algebra mistake. So the h's cancel. And what we're left with is, I'm going to write it big, is 2x plus h. So what we've done is taken the thing whose limit we want to take and done some algebra and come out with something much simpler. And so what we're going to do then is, well, they're equal, except maybe where h is 0, but h is not 0 in this process. Take the limit of one, take the limit of the other, take the limit of the other, take the limit of the one, you're going to get the same thing. So we take the limit of the easy one, and that's an easy limit, as you're about to see. So the limit, h near 0, big old nasty fraction, h on the bottom, and I'm just copying down what I've done here. So there's the original thing whose limit we were trying to take. And then that is the same as the limit of the other thing that we found that's equal to the original thing, but much simpler, 2x plus h. So the step here is, this isn't all doing limits. People try to do limits while they're getting through this, and they get all confused. So you do the algebra, and then you do the limit. You do the algebra to find something simpler, and then you, oh, I don't want to take the limit of that. That looks like it might hurt. Oh, I'll do this. Okay, if h is near 0, 2x plus h is near 2x. So that's the limit. I'll scan this so that you can study it more carefully. And I remember the first time I saw this, I was just head exploding. But with a little practice, you can get used to it. Okay, so what we have here is the derivative of x squared is 2x. I'm adding that to the little table. And I'm going to jump ahead and amend that a little bit to say that derivative of x to the n is n times x, and now we're just going to subtract 1 from the exponent. So that's what happened with x squared. We multiplied by the exponent 2, and then subtracted 1 from the exponent. Well, 2 minus 1 is 1, and most people don't write x to the 1. So, but the general pattern that's going on here is this. And let me show you how to establish it, which is one of the most important things about how derivatives behave. And this keeps coming up over and over and over again. So this is the product rule. The product rule is usually pretty mysterious until you look at it geometrically. So you want to look at the product of two things. What's the derivative of the product? There's nothing in your life that you have done that might help you figure what the derivative of the product is. A lot of people at first thought the derivative of the product should be the product of the derivatives. Wrong. So what is it really? And the key to thinking about this is realizing that every product is the area of a rectangle. So that brings the geometry into it, and the geometry really clarifies the situation quite nicely. So what I'm going to do is I'm going to draw a rectangle, and I'm going to label the sides F and G. And what we're going to do is add a little increment to F and a little increment to G and see what the new area is. That's how we're going to judge the difference in the area. We'll take the old area minus the new area, and we'll see what's going on. That'll be the change in area, right? So, Anyway, what's gone on here is this. I'm going to add a little bit to G and a little bit to F. Those aren't necessarily the same. And then I'm going to see what the new rectangle is. So the new rectangle is going to look like this. It already looks like this. Anyway, there's the new rectangle. And I'm drawing in a couple of little dotted things. So I've taken the original rectangle, that's the smallest one that you see, the FG, and I've extended it a little bit vertically and a little bit horizontally. And now I have a new rectangle that's bigger, and we want the area of the new rectangle. The F times G is the area, so the change in area will get the area of the new one minus the area of the old one. And here's what's going on. I'm going to label each of these rectangles with their area. So the original one is F times G. Now, if we look above here, the horizontal distance is F, and the vertical distance is delta G. And if we look on the side here, there's this strip, and now the horizontal distance is delta F, and the vertical distance is G. Remember, G is the original length, so this is G times delta F. And now we're going to take the big insight of Isaac Newton and say, well, we've got this third little piece here. It's little. No, it's littler than that. It's when you multiply little things together, they get super little. So we ignore it. It's not big enough to make a difference, so we ignore it. This is what Isaac Newton said. And what we find is the change in the area. I'm sorry, I wrote the wrong thing. Change in area is F times the change in G plus G times the change in F. So that's what this diagram shows you. And when we look now at the limit to what goes on, we'll find the product rule, which says the derivative of F times G is F times G prime plus F prime times G. So I've taken the limit here, and so this is the product rule. So that tells us how to do x cubed as x times x squared. And that also tells us how to do all kinds of other things. And so this formula can be established using the product rule. Product rule is one of the most important things that we use in applications, even though we don't actually do it. It's like x times f of x. What's the derivative of that? Oh, we have to use the product rule because there's a times in there. Anyway, Newton did this, and we'll do this some more. And these are all the derivatives that one takes in elementary calculus. Elementary as in periodic table of the elements, not elementary like third grade.